and they're also like interdependent. So one decision kind of cascades into other decisions, and other decisions would have been made differently depending on other decisions. So it's all interconnected. But I just sort of like put them in a somewhat arbitrary order. So like the first decision that sort of like bears discussion, I think, is if you're going to write a static verifier or some kind of static analysis engine with a view of verification, should you target the entire language or not? In the case of MIRAI, the decision was made to target the full language, the entire language. And the nice things about that is that, well, you reduce the barriers to adoption, right? So anybody writing any Rust for any purpose can run this static analysis tool over their code. They don't have to do anything or restrict themselves in any way. And it also just means that we've got a very large code base to run over. And potentially it could have become part of the standard Rust development tool suite. Negatives is that it takes a very long time and a very large investment to write a tool that targets the entire language. And so if you sort of like hit your market window, you kind of run out of runway, which is kind of what's happened to me, right? Other problems is that Rust is an extremely complicated language. It's still rapidly evolving. There's no standard for it. The semantics are kind of tricky. And the size and complexity of the language reflects in the analyzer. And so you have bugs and shortcomings and so on. So yeah, thoughts?
Yeah, I believe we have a question. Sorry.
Yeah. No, go ahead.
Go ahead, Francois.
I'm sorry. No question here.
Oh, sorry.
Yeah. So, any thoughts about this? Of like, is anybody else targeting the entire language? Do you think it's the only option, or just what do people think?
So I have a question about that, which is, is it really sort of an either or choice, right? So you can target, so for us, our goal is to target the whole language, but our idea of the way to get there is you target enough of the language to do interesting things for interesting customers. And then you keep expanding your coverage as you run into corners of the language. Like, why can't you do that?
That kind of makes sense. It's sort of like the model of saying minimal viable product and then expanding from there. And yeah, so start with a subset. For example, just safe code, no threads, no async, no foreign code. You can do sound verification of that. There's also the question of, are you going to require an annotation language, like a way of annotating your code? Because let's say, are you going to verify code, just annotated code where you've got preconditions, postconditions, invariance, all of that stuff put in? Or are you going to just analyze the language as it is? Anyway, so the compromise is that in MIRAI, we targeted the full language to lower barriers to adoptions, but we also allow you to put in explicit annotations, but it's not required. Yeah, so I think starting just with a small subset of the language and going from there can keep you in business. Not a bad idea. MIRAI was kind of like a race to try and be relevant to the project that paid for it. It was kind of made that decision. Had to go the one way.
So I have a question also about the Rust that you targeted. So I mean, you mentioned this whole MVP and then iterating and growing the language, the fragment of Rust you support. Was there a particular aspect of Rust that you found more challenging to add support for than another, or was it just the overall details and complexities and all the sort of fractal dimensions of everything?
Yeah, there were a number of things that were particularly difficult. So and so we'll get to some of that, but certainly modeling the unsafe portion of the language, where you get all of these unsafe casts and reinterpret casts, and dealing with like mutations and of pointers, and what is the thing called? So like the I mean, anyways, when you take a struct of fat point with thin pointers and you turn it into a struct of fat pointers, and all of that kind of stuff happens in the unsafe stuff. So that was extremely challenging. Took a lot of time and effort to come up with that.
Yeah. Okay. Yeah, that makes a lot of sense to me. I think Daniel, you had a question as well.
Yeah, another question. So you say you're trying to cover the full language, but Rust also has parts that sort of go outside of Rust, right? So you can have foreign function calls, you can insert assembly. What was your goal there?
So the only option really is to have a way of modeling what happens in a foreign code. We did not in this project try to integrate with other ways of analyzing the foreign code. You can imagine, and we have some slides about that, that you could analyze foreign code as well by bringing in LLVM and so on into the picture, but that was not, wasn't able to do that in this project.
François?
Yeah, there's so the overall question I want to ask is, does extracting value out of MIRAI always require annotations in the standard library as opposed to annotations in my project? And in particular, I'd like to highlight that off the top of my head, I can think of half a dozen projects in Rust which derive value from static analysis to basically call graph analysis. There's Button Queen's project on double lock and conflicting lock detection towards concurrency. There's the Merlin project in cryptography that is basically tracking Piacemia transforms. But basically, and then there's at least the Rust FSD project, which is there to track state machines. And of course, there's in the annals, historical annals of the compiler, there's the type state pattern used to track state machines. And I happen to know that MIRAI has the ability to introduce Ghost and do a little bit of state tracking. So is there a portion of value that the taint tracking, sorry, is there a portion of value we can extract from that already?
Yeah, so we can say MIRAI kind of like is a V1. It's sort of a completed usable product. And yeah, the taint tracking, which is kind of like what I'm working on at the moment again, for privacy purposes, but in the context of PHP, is a very useful tool for a lot of things. And so I think a lot of verification becomes far more interesting once you bring taint tracking to the table. So it's probably something to be very thoughtful of in any kind of project that you are working on, as hard as it relates to taint tracking. Or data flow analysis, I guess is another way of putting that. Okay, so let's maybe put a few other things on the table. So the other big decision that was made, and that was basically not the initial decision. It's kind of arrived there based on the reluctance of programmers to actually do anything proactive on their part. Is just that they were always pushing back on the fact that there are false positives. The first, like, minimal viable product portion of MIRAI, there were thousands of false positives, and everybody just immediately reacted very negatively to that. And so the project pivoted to saying, okay, let's minimize false positives. So in general, false positives are really hard to explain, particularly when they arise because of limitations of the prover or just missing parts. And then if you have to go to long hand waving and stuff like that about why this is there and why you can get around it. So people just like switch off and say, okay, this tool is not ready. And so obviously the trade-off here is that if you minimize false positives, at some point you're going to allow false negatives. And false negatives, again, has a negative impact on people's perception of the tool. So if we completely insist on soundness, you basically decrease your audience from all programmers to basically specialized programmers who care about verification and soundness.
Next meeting.
The other alternative is to increase precision. So you can reduce your false positives by just being more and more precise, but obviously we run into decidability problems and constraint problems. So generally, if you want to make the tool run quickly enough for the general population to run it, you're going to have to sacrifice precision. And so for MIRAI, basically try to do all things for all people, so you can run it in a sound mode, given some assumptions about about unsafe code, and I think there's some further assumptions in terms of aliasing that is not yet addressed. But basically, you can run fairly sound, and there are k-limits to deal with all of the resource tracking things. And so when you run soundly, at least you know when you run into a k-limit. Whereas if you're just running for normal programs, you don't want to like burden them with, oh, the solver's timed out, or the expressions got too large or something like that. I guess that's this topic. Any thoughts or input on this, or questions? What are the general feelings around false positives, false negatives, and k-limits? I know this is a fairly sound-oriented, formal verification, formal methods crowd. So, kind of, what decisions are you making and why? What do you guys think about this?
I have it's a question that's sort of, I think, more general for the abstract interpretation community, but of false negatives and false positives, is there one that you feel is more harmful to user trust, or is it just as long as you have too many of either, it's just as bad?
So false positives is your first problem. Like if you overload people with false positives, they're immediately going to switch off. If you can get them to the point where they actually adopt the tool and use it in daily thing, at some point they're going to start complaining about false negatives, because then they start, particularly if you start giving them true negatives, start fixing that, and then boom, at runtime, it turns out that there was something that was missed. That, oh, you should have caught that. And then I start getting upset about false negatives. And, another project I worked on previously, Zonkolan, which actually produces a lot of false positives, but has had, for reasons that some adoption, are suffering from people complaining about false negatives. So yeah, I suppose the hack type checker is another one of those. It also suffers false negatives, and people get upset about that now. After initially, they were all about doing reduce false negatives, false positives, reduce that. At some point, they got traction. People started adopting it. At that point, it's people get upset about false negatives. So people complaining about false negatives is the good problem to have, but you won't get there until you have eliminated enough false positives to get people to adopt the tool.
Are there any other questions? I think we can continue.
Okay. So the other thing that was decided fairly early, and that was based on my experience of Zoncolan, where the analysis is flow insensitive. And that actually leads to most of their false positives, or a great deal of their false positives. So I wanted to be more precise, so I decided to do a flow-sensitive analysis. So retaining full precision for when you join forward conditional branches. The nice thing about that is when you're dealing with simple examples, things almost always work the way you would expect. Like you are able to prove things and assertions that seems obvious and that people expect. The negative, of course, is that you are not abstracting as much, and so your complexity grows exponentially. And dealing with these branch conditions is really quite complicated. So I spend a lot of time, many months, dealing with bugs and fallout from keeping track of the flow sensitivity. But alternatives, like what was done in Zoncolan, is you just treat all joint points uniformly, and then you start putting in various AST-based heuristics to try and get rid of some of these special cases, or try and take special cases into account to get some precision back. So MIRAI is kind of a compromise that we keep track of symbolic expressions, but then there's also some abstract domains, and resort to abstraction when possible. But basically, we're just living with the complexity. So MIRAI is kind of a fairly complex tool because of flow sensitivity. I guess in the formal methods where flow sensitivity is kind of not controversial, but I'm kind of interested to hear if there's any naysayers. Is anybody arguing for being flow insensitive? Move on.
I actually have a very quick question.
Oh.
If you were to redo MIRAI today, would you still go with a flow sensitive analysis, or like, do you think that complexity has paid off?
Yes, I think so. So in my next project, which is dealing with PHP and taint tracking for PHP, it will be sort of like the anti-Zoncolan in some ways. Like, so it will be flow sensitive precisely to try and deal with some of the problems with Zoncolan. Zoncolan is a great thing in terms of like it can analyze hundreds of millions of lines of code in fixed amount of memory and quite quickly, amazingly quickly given the amount of code. But that leads up to a lot of false positives. And so one way to deal with things is, or even to validate the heuristics that they use to reduce false positives and false negatives, is to have a precise analyzer that you can run over slices of the code. And so I'm sticking with flow sensitive analysis. I'm pretty strongly in favor of flow sensitive analysis, but you do pay a considerable price in terms of complexity for it. And things that otherwise might be fixed time becomes exponential. You get path explosion. There's a lot of things you have to do in order to try and deal with the path explosion problem. So a lot of heuristics and things that work most of the time, but sometimes they don't, and it's kind of ugly. So you definitely pay a price for this, but I'll pay it again.
Okay.
Okay, so in terms of what should the analyzer do? What is the purpose of the analyzer? So in the case of MIRAI, the analyzer is very basic. It just finds panics. So there is also the taint analysis part of it, but even that has been sort of like cast into the terms of finding panics. So we're making the analyzer such a simple thing as like, it's just reporting when you can panic. You can basically find a lot of implicit correctness assertions from the codes of like all of the things that people just normally write into their code, and all of the things that the Rust compiler does for you. It just shows up as things that the analyzer can analyze and comment about. So you can do interesting things with the code without having any annotations in it, because your annotations are kind of implicit. And there's a wide variety of conventions that people do, and in terms of parameter validation and unit tests and so on. And all of these things become visible and accessible to the analyzer by just focusing on the panics. On a negative side, parameter validation versus consistency checks is kind of hard to tell apart. And so if you mistake a parameter validation for a consistency check, then you will give a diagnostic where you really have a precondition. And so even when the analysis is very precise, you can still give people results that they don't expect and don't like. Alternatives, obviously, is that you can require people to write explicit correctness assertions, and then you bring into play things like invariance and quantifiers, model fields, type state, and all of those things. Other alternatives that people often do is to make the analyzer pluggable, so that you can put it in a lot of custom heuristic-based analysis on top of the basic analysis engine. Zonkeland is a bit like that.
I believe we have a question from Daniel.
Yeah.
You're
Sorry, off mute. So my question is, if you use the existing runtime checks, Rust only runtime checks a subset of the sort of undefined behavior that you would want to be catching, right? So for example, it's undefined behavior to put an invalid bit pattern into a structure, but Rust generally doesn't have a check for that. What was your thinking about, is it worth putting additional checks for stuff that Rust doesn't runtime check, or were the runtime checks sufficient?
The runtime checks are pretty extensive. The undefined behaviors, unless there's a runtime check, so obviously MIRAI is not going to get that. So that's probably something that would need more explicit support inside the analyzer. Of course, the runtime checks is not just what the compiler puts in, but it's also what people put in implicitly by writing panics. So there's actually a lot of code that where people panic, where they essentially are writing implicit preconditions or consistency checks in the form of panics. So there's a lot more than just what the compiler gives you. But you know, if you have a more concrete and definite analysis or verification project in mind, you may want to have a specialized checker or a specialized set of annotations. So those are definitely alternatives. Okay, shall we try something else? I don't know if this is something that comes much to mind. Stuff like model checkers and partial evaluators and so on typically would do a lot of loop unrolling. So MIRAI, and my previous project to MIRAI was pre-pack, and they did extensive loop unrolling. And so for MIRAI, I made the decision not to unroll any loops. So always basically taking loop bodies to fixed points, even for fixed iterations and so on. And so the positive here is that you don't have to explain anything in terms of why some loops are precise and other loops are not. and you kind of reduce the complexity of the analyzer quite a bit. And the negative is that if you are analyzing unit tests that reason over small bits of data and then make assertions about the correctness of the unit test, then you're going to, when you analyze those unit tests, you're going to abstract with the fixed point and find yourself unable to prove the very particular concrete assertions that the unit tests make. And so then you're going to give you get a lot more false positives that way. Any thoughts about this? Well, I guess alternatives, like pre-pack, use a partial evaluator, combine a partial evaluator with a static analyzer to try and do the small cases precisely and the larger ones and abstraction. I suppose in MIRAI, the compromises is that you can reason about the state of a loop by just adding in some assumptions. So there's an assumption, a way of annotating the code of assumptions. And then a couple of very limited heuristics added to that. So in general, I didn't have too much trouble with loops in the code I've looked at so far. Anybody want to wade in here and give advice? Who would have done it differently? What are your different approaches and why? Like loops are kind of like one of the really hard things to deal with. So I think there should be a lot of opinions about it.
I think I would have done it differently in my case.
Yeah, let's hear about it.
I would have done, I mean, if you have information on the number of times you can unroll a loop, why not use it? I mean, the analysis will be more precise and simpler that way, isn't it?
Yeah, I actually agree. It's like if the loop is fixed, why not do that? It actually doesn't make the analysis simpler. It adds complexity analysis because you always have to deal with the case where you don't know the bounds of the loop. But you will get more precise results. But it does make the analyzer a lot more complicated. But I think in my next project, I probably will unroll loops as a matter of course up to a K limit.
Yeah, I mean, if you cannot unroll loops for some reason because you don't know the bounds, that's completely fine, I think. But if you have that information, I would say use it. Yeah.
I think it's important to always have a K limit because if the loop does 10,000 iterations and there are such loops, you can't really afford to do that. And particularly when the loops go over heap structures that you also had to abstract over because of other loops and so on, or because of some external loop or callback to the various reasons why even fixed loops cannot be analyzed precisely. So there's this limited value that you get out of it, but it's certainly, I think I will explore it again in my next project. I intend to. So who's done it? So like who's actually done loop unrolling and what were your experience?
Actually, by default, loop unrolling is what we do in Canny because we're going to a bounded model checker in the back end. And so, yeah, our experience is you need the user to bound the size of their inputs. And so you then end up limited in sort of what you can prove because you need to prove over bounded inputs. But it's often true, and this same matches the experience with C, that in fact, if you can prove a property for small inputs, that property tends to hold for larger structures as well. That's not always true, but it's often sort of something we've seen to be
Yeah.
true in practice.
No, I quite agree with that. Like, once you get to like to 10 iterations, it's probably not anything that you will prove of 10,000 or 10 million that you want to get with the 10. Yeah.
Yeah. So as a formal methods person, it doesn't feel great to say, oh, we've only proven it up to a bound, but in terms of the actual assurance that the customer gets, it ends up being pretty good.
Yeah, so when you don't know the bounds precisely, when the bounds are not fixed, it becomes tricky when you take it all, when you always execute a loop 10 times, even when the loop wasn't meant to ever go that far. So you probably need to be somewhat more careful about unknown bounds.
So I had a question about your architecture.
Mm-hmm.
Right, so I'd been a little surprised to hear that doing the unwinding sort of raised the complexity of loop handling, because I had imagined that being sort of that there's an unwinding pass, and then, you know, once you've done your unwinding pass, then you do your fixed point pass. Are they sort of conflate, like, are they sort of like one loop handling code, or is it pass based, or sort of what made it more complex to do both?
I guess for part of what made it more complex is that I just directly interpret MIR as it is, without any kind of attempt at being able to rewrite it or inline or unroll or do any of that stuff. So if you sort of like build your own intermediate language and you have nice ways of mutating it and dealing with that, it would probably be easier. My decision just to use this like MIR in a read-only fashion as is probably made my life more difficult in this respect.
And my other question, does it matter sort of what kinds of loops people use, right? So like in Rust, you can write explicit loops, but you can also write, you know, you can write maps and folds over structures.
Yes.
Did that make a difference?
Absolutely. Yeah, so dealing with recursive loops is a little bit different from dealing with control flow loops within the body of a function. So that also makes a difference, yes.
I think we also have, Leo, do you want to go ahead?
Yeah, hi, can you hear me?
Yes.
Cool. Yeah, about the loop question. So I currently work with constraint horn clauses and horn solvers. And so when I encode loops, I just encode them as is, as they are using horn clauses. And I feel like with loops that have constant bounds, the solver is usually able to just detect that and make it solver for itself and make it easier for itself, as opposed to like a completely unbounded loop. I was wondering if in your solution or in a bounded model checker way, you could have a solution where you don't have to try to identify the constant bounds before the more generic algorithm comes and tries to solve the whole thing.
I don't really have an answer for that, but I think you do raise an interesting point as well. This is that constant bounds, when they depend, when the analysis depends on constant bounds being known, but you're computing them from the analysis, then you kind of like have this need to do several passes and constraints about having one pass or another, and that also that does add complexity. Just doing sort of like a single analysis step, maybe with fixed point loop, but basically doing a comprehensive single analysis step all at once, like simplifies things conceptually, other than trying to say first do constant and then do something else. If the solver takes care of all of these things under the covers, it makes your life a lot easier.
I had a quick question, which I think is related to Daniel's last question, which is, does MIRAI handle for loops? So in iterators where, I mean, there is a syntactic loop even, you know, in the CFG of the mirror, but it's, you don't really see that, you don't necessarily see the actual underlying mutation of whatever your loop index is. You just get a new value out from the next call.
Yeah, so when you have these higher order recursive loops, because it constructs summaries that are specialized with respect to the function parameters, and it does deal with recursive loops, and so you eventually end up with a recursive loop somewhere, and because you're passing in the function parameters, you end up inlining those. So it does actually, it is able to reason to some extent over these recursive loops. That was the big motivation for making sure that everything gets inlined and resolved. Because if you don't do that, you very quickly run into a lot of diagnostics and false positives around recursive loops, which I've been able to suppress most of that quite successfully using this technique of always resolving calls because of this problem.
All right, thank you.
Yeah, so to maybe give an advert, so at the end of the project, I was able to take the entire blockchain code base from Novi and run MIRAI over it in its default mode, and it would successfully analyze each one of those crates, terminate, and produce no diagnostics. I had to do I added some annotations, a few annotations, but basically successfully inferred enough information to not give any false positives after a modest amount of annotation. There's some chat. Okay, fine as well. Okay, so let's go back. See, I missed out on this. So the other big decision, but one of the decisions I made, which was in contrast to my previous project, where we started out with an existing interpreter for JavaScript and turned that into a partial evaluator and then into an abstract interpreter, and sort of just by adding more stuff to it. So that basically had a very classical heap model of modeling everything as explicit objects and pointers from one to the other. Whereas in MIRAI, the heap is modeled as a flat list of path value pairs. It's a flat set. And so the paths in this model closely resembles the place concept in Mir. The problem, of course, of this, and well, most heap models, is what to do with aliasing. And the other problem is like values. What do you do when values are structured, and so on. So the positives of this is that you can sort of like use a single environment to track local variables, parameters, and everything in the heap, and joins are pretty straightforward. It's also a sparse representation of memory. So it's nice to use in summaries. And so the memory consumption of the heap model doesn't really go out very bad, doesn't grow much. The negative is that the heap model is only really accurate when there's no aliasing. And so when you're updating the heap model, you have to go to a lot of trouble to try and ensure that there's no aliasing going on. So there's a lot of path canonicalization and weak updates, and some of that logic gets very ugly, and it's also unbounded in complexity, and it's been a bug farm. Mir doesn't make it easy either, because Mir doesn't really keep everything simple. So at some points, a path can denote an entire collection or structure rather than a simple value. And particularly when you are dealing with parameters, we don't know the value of the parameter. This becomes a problem. And then we have transmutational values, which is also very tricky to deal with in this model. Like, it's on the whole hard for me, at least, to think of good alternatives to using this flat set of value pairs. Mentioned prepack already. Of course, if you look at MIRAI is using a different heap model. One might try to do it that way, but it doesn't really seem like a good alternative. I don't know. So, what do you guys think about heap modeling in general? So, like, how are you doing it? And does somebody have particular success with a heap model? I'd kind of like to know about this, particularly in terms of my next project. Like, was this the wrong decision? Would you do it differently? Do you have a good alternative? Just in general, what are the thoughts about heap models?
I know that Yusuke is with us tonight, and he wrote a great paper on his tool called Rusthorn, where one of the big contributions is a technique that he uses to sort of avoid having an explicit heap model for verifying Rust programs. And it's one that I use in my tool as well. And so I think I mean, I don't know how applicable it is to your requirements in abstract interpretation, but it's a quite neat approach, which can be called sort of a prophetic encoding, which exploits the uniqueness of mutable borrows by representing them as a pair of an initial or current value and a final value at the end of the lifetime, and placing appropriate constraints to ensure that there's no unsoundness in this encoding. But I mean, if Yusuke wants to pop in, I mean, and no pressure, so sorry. But I know that in his paper, that's one of the big things, is that he's able to achieve much better performances than with a traditional kind of encoding.
So to put some pressure on him, like, so for my next project, should I read your paper, and should I can I expect to do a precise analysis for PHP using the techniques in that paper without having a heap model?
I would be surprised, as it very heavily relies on the ownership typing of Rust. So it's really about leveraging those the uniqueness of those mutable borrows. But hey, maybe if you add a new type system to PHP.
Oh yeah, people are doing that, of course. Not another one, I don't know. But yeah, so yeah, let's have like a free fall here, like a jump in. Like, somebody must have an opinion. This is kind of one of the most important things in static analysis, how to deal with the heaps. So let's have a discussion here.
I mean, if I can add another question for you, I'm curious what you do about types with interior mutability, like cell. Do they complicate your reasoning about the heap at all, or does it work fairly naturally?
Well, because you are modeling the heap at the field level, essentially. So, and you also include side effects on the heap in the summary of a function. You do track those things. So the one thing that should be done, that I intended to do all along, but I haven't gotten around to, and it doesn't appear to be so important, is if the caller calls you with two mutable pointers, or with two pointers which are not mutable, which alias each other, but they turn out to be something like a cell, and you unwrap them, thinking that they are distinct. You can, in principle, by looking at the side effects and seeing that there are two side effects that after call site specialization turn out to be aliases, then you can detect that and give a diagnostic for that, but I haven't actually done that.
Yeah, because I think, I mean, that's a big, I think it's a big issue for the deductive verification tools that exist today. I know my tool, Clouseau, doesn't really have, we have a solution, but it's not a very satisfactory one. And I don't know if Prusty, which is the tool developed at ETH Zurich, has a good answer to the question of interior mutability as well. Yeah.
So no free fall here. So this is a very, very mellow crowd. People should be shouting by now. But okay, let's carry on. We're kind of running out of time, so we're gonna. I have a hard stop at 11. So let's see. So I think maybe this is the important one. Precondition inference, and it'll be the last topic. You were saying?
No, I was just saying, I think you have time for one more topic. We don't have to be exactly on the dot, but yeah, we'll.
So, to my mind, precondition inference is one of the most important things to do, particularly in terms of reducing the annotation burden and reducing false positives. So basically, when MIRAI analyzes a function body, at some point it gets to a panic, and it determines from its flow sensitivity and path tracking that this path is actually alive. It's a feasible path. Then it will want to give a diagnostic, but rather than, but so it could be that this path is only feasible given a particular parameter value. So a possibility is that this panic is actually part of a parameter validation check. So by default, if you can reduce the path condition leading up to the panic to a condition that is completely controlled by the caller in terms of parameter values, then that reduced condition will be regarded as a precondition that prevents you from reaching this panic, and it then becomes an inferred precondition. So there's a lot of positives for this. The positives mainly that the false positives are reduced quite dramatically if you treat every panic that can be reduced by prevented by a parameter value as being not an actual diagnostic, but a parameter validation check. So this drastically reduces the false positives. And so I think any analysis tool should put in a considerable amount of effort to do precondition inference. The negatives is that extracting the precondition out of the path condition is a tricky business. It's very heuristic based, and you can end up with preconditions that are actually so stringent that the caller cannot uphold them, and because you can't tell just from the code, particularly at the mere level, whether something was intended as a parameter validation check or where it's actually a more complicated condition. This happens to also include a parameter value. If when you do this, you can end up with unsatisfiable preconditions. So yeah, so I'm gonna have to bail out in a minute. But this is probably one of the things that are best thinking about very carefully is how you infer preconditions. That's very important, a very important matter.
Well,
in my experience of this tool and other tools.
Well, thank you very much for sharing your insight and the lessons and compromises that you had to make while developing MIRAI. If you have to leave, of course, don't let us hold you back. But if there are any very quick final questions, maybe I see there's Pointer Bender asking how long you worked on MIRAI for.
It was 3 years in total, but it was just me. It could have been quicker, I guess, with more help. But there was also some iteration. We didn't come up with the final set of decisions initially. There was a lot of exploring of alternative paths.
Yeah.
Okay, so I got a bail,
All right.
unfortunately.
Yeah.
I've got another meeting to
All right.
run to.
Well, thank you very much.
Well, thanks everybody.
Yeah. And everybody will meet back up in February, and we'll hear a bit about the lessons learned in Ferrocene. All right. We'll see you next month.
Bye.